Well, we might as well get going with this. A couple of things I wanted to spend time with tonight was an alternative method of doing flavor analysis. We've spent a fair amount of time on that. But there's a different approach, one that I think is rather fascinating. And so I want to spend a little bit of time on it. And then, oh darn, there's a second subject. We'll find that when I get to it. How's that? It must be important. Anyway, okay, so let's go ahead. This is Josephine Sharp, who is a PhD in laboratory. And so I kind of took her presentation and tailor-made it a little bit more for us. So anyway, let's go ahead and have a go with this. And I think every field you work in, there's some holy grail, some goal you really want to accomplish that would have a significant effect on that particular area. And for us in the flavor field, the flavor chemistry field specifically, a holy grail is actually to characterize the flavor of food, chemically characterize the flavor of food. And so if we were able to know exactly what we need to deliver, what concentrations to have a quality, and I find quality flavor, would be extremely valuable. The idea of standardizing food flavor across different manufacturing locations, different countries, different ingredients. So a company may be able to say, hey, this is the profile I need. This gives me that profile. Okay, I'm in good shape. The idea of troubleshooting, so in terms of stability issues, if something's gone wrong with that flavor, it really helps to know these are the chemicals you should have and they should be in this proportion. If they're not, okay, then you can start saying this is probably what went wrong. So the idea of stabilizing the flavor, what do we need to stabilize it, what is quality, is increasing flavor intensity, what do we need to increase to make it taste good yet, but be stronger in flavor? Understanding pathways, chemistry, flavor development, packaging, flavor, food interactions. There's just all kinds of reasons why we'd like to understand, like I say, what is needed in a food to make it taste the way it does. What compounds and at what concentrations. And I think when I was talking about the flavor earlier, analytical flavor, I think I mentioned not one food is, do we know that? I don't care what food it is. There isn't one food that we have that information thus far in life. And it may seem surprising because we've been working on this for 50, 60 years, and we still haven't been able to do it for all global effort. And so this is, I think, a little different direction in that area. And so let's kind of see where it takes us. As I said, we're over 50 years we've been working in chemistry flavor. The advent of gas chromatography, mass spectrometry came along. All of a sudden we were able to start getting some look at the chemicals that give food its flavor. Now 50 years you might say that's pretty old. Well, actually it isn't. There are many fields that are much older. 50 years of research is still kind of young in many areas. But anyway, like I say, we've been doing this, and we've been doing it in certain ways, and they haven't yielded success to us. And one problem that we've had, I've mentioned also before, that historically, we've analytically looked at aroma. We haven't looked at taste. We've assumed that aroma was all there is. And lo and behold, oh darn, food does have a taste to it. Once you know, they interact. And so the idea that let's start looking a little more broadly. And even the idea that we can look at aroma, we can look at taste. We still understand that there's more to it than that. And one of the figures that I showed you at least one point before was that really that idea of perception takes into a lot of different things. Olfaction, appearance, what do we expect food to taste like? So the heat, the cooling, the sound, the crunch. Are things right if it doesn't have a crunch? You can expect potato chips to have a crunch. If it goes squish, there's something wrong with it. Would I say that's something wrong with flavor? It probably changes how I perceive that flavor. So taste, smell, feel. So again, we need to look much more broadly at inputs in terms of coming up with some kind of description or characterization of flavor. And so we really have, I would say, a long ways to go at this stage. But the idea is, how do we take chemical data and link it to perception? That is, chemically define the stimuli that we really need in a food. And so we need a different method. We need something more than looking at aroma over here, looking at taste over here, looking at other aspects of flavor. We can't look at them independently. We have to look at how they interact, how they work together to create some flavor image in our mind. And so that's basically what we set out at. And I look at that slide and say, wait a minute, what's that have to do with what we're doing? Did I mention, I might have told you this already, I'm going to American Society of Mass Spectrometry, sitting in on the presentations on mass spectrometry and heart attacks. Does it ring a bell? Oh, good, then I won't tell you the same story twice. Okay. So when I go to meetings, I like to go to meetings I know nothing about. I learn so much more. And so here I'm sitting in with a bunch of medical doctors and researchers listening to a presentation on silent heart attacks. I thought, that's rather interesting. And what they wanted to do is they wanted to go to use analytical methodology to determine if a person has had a heart attack. If they had a heart attack, but there really wasn't symptoms to it, so nobody recognized their symptoms, that person was more likely to have a heart attack again. So there'd be some advantage in being able to know, has this person had a heart attack? And they were doing this by analyzing the breath, the blood, the urine, basically any tissue, any excretion that there is, and collecting data from this, and could go ahead and link this to having a heart attack. I'm really not interested in having a heart attack. That's not my goals. I'm really not interested in looking at other people's heart attacks. But I'm interested if something tastes good. I'm interested if it tastes more green. I'm interested in these kinds of things. And so if somebody can collect all this data, put it together, predict heart attacks, I should be able to predict something, whether it's green or cooked or birds or whatever it is. And so basically, I took a look at what they were doing and said, I want to do this in flavor and try to use a better combination of data, analytical data, to predict something. And so that is what I set out to do. And like I said, Josephine was the student who got the opportunity to work on that. And so chemometrics is, now this slide probably didn't look like this. Oh, there's more parts to it. Here we go. Okay. I was wondering what happened. It lost something. And this is a little bit of an add-on to you. Historically, when we've looked at measuring aroma, measuring taste, measuring various components of flavor, we're hypothesis driven. We make some assumptions. We assume in the case of this aroma extract dilution analysis or AEDA that there's a certain relationship between this data and some perception. And we kind of make that hypothesis. We assume if something smells greater at the end of a gas chromatograph, we've done a beautiful extraction of flavor out of this food, and we sit there, take it apart one by one, and smell them as they come out of a gas chromatograph. Oh, there's one, that's a big peak, and oh, that's strong. We hypothesize this is important. We hypothesize that this is going to be significant. And that isn't always the case, and that's what gets us in trouble. I think I've lamented the fact that we have such poor methodologies to really do that kind of work, to draw these kinds of conclusions. But that's what we've been doing, basically hypothesis-driven research in this area. We assume there are relationships, and then we test that hypothesis. But I like the idea of what they were doing with the heart attack. They didn't make any assumptions. What they did is they just gathered every bit of data they could. So it's data-driven, non-targeted. And so working this direction, data-driven, non-targeted, all instrumental data are collected. We don't assume that anything is irrelevant. And really, we don't get into this restricted earlier thinking about there must be a relationship between these or so on. And so that's the whole idea. Multidisciplinary, chemometric. Instead of flavoromics, I could have called it chemometrics. That's what it is. We're linking a massive data set to some outcome. And that's certainly a popular field. It's been popular for a long time. It just hasn't been applied in this particular area. And so that's what we set out to do. And I call it flavoromics. I could have called it chemometrics. I thought at this point there was metabolomics, there was proteomics, there was a lot of things. We should have a flavoromics. So that's what I chose to call it. How's that? If you search it, you'll probably find something on it. So we do have to keep in mind that these are statistical tools. And so the idea that there is a statistical correlation, I'll point this out later on, at least we start off with that. And so we got to also keep in mind data doesn't mean information. Data in itself doesn't mean it's information. It's simply data until you start that interpretation. You start having it take you someplace. You will notice, I think there's notes in the slides that you have. Yeah. And so if I missed anything, okay, it's there. And so what I saw for taking this particular approach is two particular aspects to it. One, people have been doing this for a long time. They would love to get rid of sensory panels. Sensory panels are a pain in the neck, right? They take a lot of money, they take a lot of time, they take a lot of people. Problem is they give good information. There's been no other way to get that information, and there still isn't any way to get that information. But, this has been done. This has been tried for some time, looking at data sets and making sensory predictions. So linking chemical stimuli to perception. So yeah, that's not my goal. What I'm interested in, I'm interested in discovering something. I'm interested in discovering something that isn't known, some relationships. And so one of my problems about the same time is I was struggling with the idea, what is fresh? Does food taste fresh or doesn't taste fresh? How do you study fresh? How do you quantify it? What do you measure? And if we decide we're going to take a nice fresh food out of the oven and compare it to something that's been sitting out for a while, we might do a nice aroma isolation in both cases and do our nice rigorous analytical work. And we get some extracts, and we sit at the end of a gas chematograph, because that's what we tend to do. Use a person sitting at the end of the gas chematograph, and I tell you, I want you to look for fresh. Tell me if you smell something fresh, because my hypothesis is that there are components in there that make it smell fresh. So what's fresh smell like? Any idea? I don't have the foggiest idea what I would smell for. What is this fresh smelling component? Is a fresh smelling component the same in bread as it is in strawberries or in something else? And so I didn't have a way to study what is fresh. And people want fresh. Is it a lack of off-flavor components? Is it some highly volatile? And so my goal was to actually eventually using this kind of multivariate techniques, gathering all the data, and then, of course, going through the sensory panels and so on, data collection, to say what's linked, what chemicals, what compounds are linked to a consumer saying this is fresh. And so that was one of my motivations really for going this direction. Discovery things we haven't been able to find by other methodologies. There's a number of restrictions in setting off on this goal. I need data. I need tons of data. I need every bit of data that you could ever conceive that might influence a person's opinion of food. So we'll sit down and we say, how are we going to get this analytical data? And that means multiple analytical platforms. You don't use gas chromatography, you don't use liquid chromatography. You use both of them, and you look for any other methodology that you can use. And so we have to use multiple analytical platforms to look at other potential inputs into what might change perception. They have to be, unfortunately, sensitive. Because people are darn sensitive. You know, when we talk about a person being able to smell one drop of the thoxypyrazine in 12 million gallons of water, am I going to get 12 million gallons of water trying to extract that out so I got my drop of flavor to work with? Not too likely. And so sensitivity. So whatever methods I choose to use, they're going to have to be sensitive. They're going to have to be comprehensive. And right away, we're starting to get opposites. Sensitive and comprehensive. I want everything. And then I want rapid throughput too, by the way. I don't want to spend more than a couple hours on this. So, okay, and again, you know as well as I do, speed is the opposite of sensitive. It's the opposite of comprehensive. So you're really asking for you're putting some severe limitations on your methodology. And so we also have to have samples that have variability, because I need a range of samples that have the attributes I want, and I need those that don't have those attributes I'm looking for. In this particular study where Josephine was doing her PhD, we were looking at oranges. So a crop of oranges are a type of orange that isn't typically used as juice. And so you'll see later on we got some help from research groups in Florida to take a look at some product there. But also I went to Pepsi-Cola. And Pepsi-Cola, I think they own Tropicana, don't they? Yeah. And so, okay, but they're also in the business. And I said, do you have a bunch of samples that you must get samples in for quality control. You must be doing sensory on these. So if you've got them and you've got sensory data, send me some. I want to put all the analytical I can to it. And the frustrating thing is that, as it turned out, they didn't have any bad samples. They didn't have diversity in their samples, because if it didn't meet their specs, they tossed it. They only kept the ones that were uniform and the product they delivered. So I really thought I had it made. I thought I had the sensory done on these things and samples available. And so they didn't meet it in terms of diversity or the variability, so I can start narrowing this down. So we have to have all of these things, which are, like I say, compromises. We have to have a variability in samples. That usually isn't a problem, but it wasn't what I thought wasn't going to be a problem. And we got to be able to handle massive amounts of data. We got to have the techniques to manage these things. And I'm just ever thankful for the medical field. The medical field gives me more than anybody else ever does. Why? Medical field has money. Medical field can pay for development. They can pay for techniques. They can pay for new instrumentation. And then I can come along and use it. How's that? Because they're not going to do it for me. Believe me. Our equipment manufacturers aren't going to set out and say, well, Gary would like this. But if the medical profession research group says they need it, it happens. And so the data handling really came along, as I said, through the medical field. And so what was our approach? We dealt largely with two techniques. We dealt with non-volatiles. Non-volatiles, that's been expanded and now in recent times, but for this particular study that started, we did volatiles, and we used solid phase microextraction. Why? Because it's fast, it's simple, crummy methodology. I wish you never would have gone this route, but okay, when it's kind of done, you're halfway through, you realize your errors, you can't change it. So okay, stir bar, don't do that. Don't do SPME. Work with stir bar. I think I tried to impress upon you stir bar is better than SPME. We'll talk about it. Stir bar would have given us a lot more data and better data. But this was so simple, so easy, and everybody was using it. Bad decision on my part. And so we want to use headspace. Why? Because headspace is fast. So again, large amounts of data, rapid gathering of data. And so we did it by headspace analysis, coupled into a GC time-of-flight mass spectrometer. And so what we collected was, the GC feeds the mass spectrometer. So we make our injection time 0, and then we start off counting off the seconds for however long this runs, 40 minutes, 50 minutes. And as every minute, the mass spectrometer is collecting all the ions that happens to see in every scan. So it's taking many scans a second. A tremendous amount of data on this if you think about it. Maybe it scans 100 times a second. Maybe we've got how many 100 seconds. And then each scan is so large. So anyway, but we collect information on what's in the vapor phase, in the air phase. For non-volatiles, it's LC, so liquid chromatography. Solid phase extraction, that's one way to go ahead and separate polar, non-polar taste compounds. Is running it through a preliminary solid phase extraction column. And so we get what we lose from that column, we get the wash of that column. The wash of the column tends to be more polar materials. The elute from that column gives us more non-polar. And so then again, this feeds into a mass spectrometer where we look at all positive ions and all negative ions. So again, we're actually looking at both ion fragments. And so we scan from 50 up to 1500, and we get the same kind of thing. Every second, we take 100 scans, and we do this for up to an hour for some of those analyses. And so, like I say, we've at this point, we've got a good deal of data that comes out of it. So we collect the data from GC and from mass spectrometry. So we've got all of our peaks that come along. We've also got all of our mass spec to go along with that. We've got a retention time, and we have a mass spectral profile. And so we start putting these into a database. And that's where it gets rather interesting too. How much noise is there? What's relevant? What's duplication? How do we make one sample equal to another sample? Normalization idea. There's duplicity in some cases of the data, averaging, centering, scaling. So all of this manipulation of those data so you can feed it into the software programs. That's one of the real challenges, the pre-processing of the data to end up with variables then. And that's what we ended up with for the gas chromatography headspace data. We had 9,420 variables that after going through this process, we went down to 134. Reverse phase negative LC, 1,116. We condensed down to 439. So overall, we had, if you kind of total up these numbers, these are the variables that ultimately we worked with in trying to draw correlations to the sensory panel. And so, whoops, this was mandarin juice. I said orange, okay, mandarin. And so we went this direction. At the same time, the group in Florida went this direction, so doing descriptive sensory analysis, looking for the flavor attributes. And so they recruited a panel, 13 to 15 subjects. That was the USDA, IRS, Citrus Labs. Generated, of course, recruited the panel, generated a lexicon, evaluated judges and a lexicon, spent 20 hours for each year on training, 19 descriptors, taste and aroma. Basically, they had to run this test over 2 seasons because what I think we were talking about at one point, hopefully, is that there's a flavor, the flavor of a product changes from year to year. It depends upon the rain, depends upon the temperatures, depends upon the soil. And so they didn't want to take one crop and say that that's representative. But of course, they did over two crops. That's not much either. But the idea of having a trained panel and going through this every year is rather expensive. So they at least took 2 crops and they went through this. And again, did their scoring on these juices. And so the next step of this whole thing was going ahead and saying, okay, we've got a set of data, chemical data here, a set of flavor attributes there, and you start looking at how you put those together. So developing predictive models. What can you come up with on this? And partial least squares, probably some of you are familiar, probably more familiar than I am. But basically, you're looking at a mathematical model that finds linear relationships between you've got this massive data set, it serves the massive data set, looking for some instrumental data that correlates or predicts sensory score, follows that along. And so basically find directions of X are chemical data, predictive of Y. And so you're basically looking for these correlations. And again, reminding correlation does not mean causative at this point. And so, oops, don't go away. Improved prediction performances, merging all instrumental data into one single data set. Best model with combined data variable selection had 576 instrumental variables. So starting to put, like I say, these two data sets together. Then you come up with a model, then the next step is validation. And we did that simply as an external. So there were 46 juices we had, 46 different mandarin juices. And used 38 to develop the model. And then 8 other samples that we used them to test basically our model. Does our model predict the sensory outcome on those 8 samples? And this is an example in this case. So looking at, I forget, maybe it will tell me which 2 variables, what's the sensory and instrumental data. I think comes up later if it doesn't come up there. Okay. And you've all seen these plots. And they'll look the same or they won't look the same. But so these are 4 different varieties of the orange. And so here are the sensory attributes. And the profile sensory panel gives this profile, predicted by partial least squares give this profile. In some cases, they're quite good, and generally they're quite good. Of course, then whenever I see these things, I'd like to see them do a triangle test or something and say, can they really tell a difference? They may look really good on those attributes. Does that mean they taste the same? I don't ever think I've seen them do that. Is actually put it together and say, okay, can we tell a difference? If you look at someone, like I say, this really looks good. But could you distinguish that? To me, that would be an interesting one, running a triangle test on it or something equivalent. But so from a prediction standpoint, it really looks quite interesting. So those data did a fairly decent job. But then the next question gets into learning. So what do we learn from this? And then we start looking, okay, let's go ahead and look at our markers, the variables that we selected, and can we find information from this? And we're going to take a really, really simple one, because if the system doesn't work for something really simple, it's probably not going to work for something more complex. And so what we simply said, okay, orange, okay, the sour attribute. So what variables were positively linked with sour perception? And which ones really were counter to that? I don't know if we can call anti-sour. How's that? And so what are these compounds? So the compound that's the biggest predictor of sour, what is that? I was just really interested, what's the biggest predictor of fresh? Okay. Then I'd try to look for this relationship and say what's linked and what's contrary to it. But okay, we really wanted the basis. Let's do something simple. And so we go ahead and say, what is this compound that was maybe responsible for this data point? And you could probably guess that. Anybody want to guess in oranges what best linked to sourness? Citric acid, yes. But of course, you do it the hard way. You see if can the machine come up with the same choice. And so you go to the mass spectrum of that compound, of that variable, and look for identification, mass spectrometry, retention time indices, MS labeling. You can go in more complicated, accurate mass work. You can do MS analysis. If you got a guess, you actually get a standard of it, give a shot into the gas chromatograph, mass spectrometer, give it to the sensory panel, say, oh, we're all in agreement. Okay. And what would that be? Of course, citric acid. Like I say, that's an awful lot of work to find out something you already knew. But what about those other things? What were they doing? Some others were really negatively correlated to sourness. Would this mean they're somehow suppressing sour sensation? Is there an anti-sour component, a blocker of bitter or sourness? So it opens doors to finding things and looking at them. What sense do they make? And so this was what looked at it for taste. And we also looked, for flavor, so aroma, I should say. And again, what were those that were strongest linked to sensory perception? So fruitiness, what was the choice there? Ethyl butanoate. If we look at more orange character, it was actually the linseed, which is also well known. So it gave us the right choices for those things that we expected. If it didn't, well, then you kind of say that didn't work so well. I got a however. Where's that taking us? Okay. The idea, and again, you keep on saying that correlations are not causative. Then you have to go ahead and do the work on it and say, okay, if I add this, does that perception increase? And the critical selection of the likely candidates, but you still have to validate it. And like I say, because something's correlated doesn't really mean that it's important to you. So you got to test that. And again, that's back to sound sensory methods. I'm rather fascinated and happy. How's that? That the Flavor Research and Education Center, which is fondly known as FREC, F-R-E-C, moved to Ohio State now, must be 4 or 5 years ago at this point. And actually 60% of their work uses this methodology because others aren't using it. The first paper we published on it was rejected by 4 journals because it didn't fit into everybody else's conceived ideas of how things are done. It didn't fit tradition. But now, like I say, it's become one of the major methodologies that we're seeing used. So it's really fun to do something like that. So anyway, that's the Flavor Center has used that technique very well. They've been able to find things, relationships, compounds that modify flavor that you wouldn't have found otherwise. And so it is helping in discovery. It's leading to things that, like I say, has made the center very, very successful. Well, let me see how I get out of this. Do you have any questions or comments?
I have a question.
Sure.
So when you're looking at those, like the spider maps, lack of a better word, but
Yeah.
when you say like you want to do a triangle test too, like what would somebody being able to differentiate the two products do to like help further prove this? I guess like if they're still mapping on like all these characteristics like relatively similar, why does it matter if they're the same or different?
Well, okay. I'm a hard person to convince of things, okay? I don't care if these attributes are all matched. The attributes. Does that mean that every other attribute or everything that might have influenced perception matches? To me, something has to pass the test, blindfolded, bag over your head, can't see the color, can't do anything, taste it. Can you tell the difference between? I've never accepted that if you match all the attributes, it's going to be an identical product. You may choose to disagree with me.
Yeah, no, I guess I also agree, but I don't know that it matters if they're identical. Like, is that, I guess that to me is not necessarily what it's saying, is that they're identical, but that they're identical on these attributes.
No, that's your interpretation.
Yeah.
Because yours says it's you know that.
Yeah. So I guess a lot of people looking at
say,
that,
it's
they're exactly the same. Okay.
It's absolutely perfect. And I don't buy that.
Yeah.
But
That makes sense.
it says they match those attributes,
Yeah.
not
whatever else isn't being asked about. Yeah.
So we're going to go into adulteration. So adulteration. Does that exist in the flavor industry? Well, it certainly has existed in the flavor industry. I think I have a strange sense of humor, I guess, sometimes. I'm amused by some things that I probably shouldn't be amused by. But if you go to the flavor industry and historically, does adulteration happen? No. No, never happens. No, it doesn't happen. And like we ran a symposium, or not wasn't a symposium, it was a session on adulteration. And that was the most successful short course workshop the American Chemical Society of anyone that's been offered in the flavor industry. And I'm somehow betting that half of the people in attendance were the adulterers, and half were the police trying to catch the adulterers. It happens. And again, maybe that's my disappointment in the human race. My opinion is if there's money to be made, there's usually someone willing to take that money. And there's tremendous money in the adulteration of flavors. They're high value products. And if you can cut costs by adulteration, I think there's someone willing to do that. My example was a long time ago when benzaldehyde, I think I mentioned that when we talked about materials. Benzaldehyde is being used by Coca-Cola for cherry Coke for many different beverages. All natural label all over it because the benzaldehyde they bought was supposedly natural. And there wasn't one drop of natural benzaldehyde sold globally. Every bit of it was adulterated because it was provided by two companies. They got together and said, we can sell this and we can make really good money. And so it's, like I say, I just think there's someone around willing to take it. And so there isn't a police department that goes around and looks for it. The Food and Drug Administration, they don't check for adulteration. That's not their job. They're interested in is it safe. That's their number one concern. And adulterated flavors are not unsafe. They're as safe as the natural flavors, maybe even safer. And so there isn't a police force that goes around and looks for adulteration. What is the police force are competing companies. I think probably my last slide in here that says one of the best indicators of adulteration is it's too good to be true. I can get vanilla for, gosh, only 70% or, of what vanilla beans cost. I think, how can you only pay 70% of what the vanilla beans cost? If the price is too good to be true, it's probably too good to be true. A company will oftentimes refuse to duplicate a flavor, but in that situation, working in the flavor industry. And they'll get a flavor in and want to duplicate that flavor at this price, and you look at it and say, that's impossible. The ingredients cost more. And if you're smart, you pass on and say, no, I'm not gonna try to duplicate that flavor. And you might then pass along to the customer that's inquiring, are you sure that's not adulterated? Also, so you want them to be looking at it. So it's an interesting challenge, adulteration, particularly for flavor compounds, because the adulterant compounds are identical to those in nature. So how do you differentiate? How do you analytically prove that somebody's has adulterated a flavoring? And so we'll go through some of the approaches that people take to try and say or prove that something's adulterated or not. And there are different reasons or reasons we care about adulteration. One is economics. Come on, somebody's selling it for this or paying this. They're being ripped off if they're not getting the real thing. Labeling reasons. If you're in an ethical company, and I've always liked Ocean Spray. Who knows where they are in the world, but I felt they were an ethical company. And if they're nailed to the wall by someone because they're selling adulterated products, what does that do to their brand? Oh, Ocean Spray. Nobody goes back and says, what flavor company did that? Customers don't know who the flavor companies are, but they know Ocean Spray. Okay, so you're protecting your brand as well, very much so. So you worry about paying for things you're not getting. You worry about the liability to your brand. So, and the ethical, yeah, it is ethical. So it's not right. There's no health concerns. It just isn't. It isn't the right thing. And like I say, there's no policing done by the Food and Drug Administration on this. It is done by the industry. The industry looks after, kind of points the finger at each other. You shouldn't be doing that. You're doing that. So it's kind of interesting. Examples of adulteration: addition of an artificial chemical to a natural product. Vanillin, for example, adulters for vanilla. And there's much more vanilla soap than there are vanilla beans grown globally. We have much more natural vanilla soap than there is beans grown in the world. So, vanillin, okay, that's an artificial chemical. Can be artificial instead of natural. Benzaldehyde, that's what I talked about for cherry Coke. Okay. Merrily, which is a beautiful floral orange blossom. You walk into an orange grove in the spring where they're blossoming. It's about as close to heaven as I'll ever get. It's absolutely fantastic aroma. Valuable product for foods. So one is using artificial chemicals instead of natural chemicals. You can also, if you look at essential oils, large market in essential oils, well, maybe you can go ahead and put a less expensive oil into a more expensive oil. And we got an example of that coming up. Some oils are cheap, they're not. Different plants. They're similar, but they're not identical. They're really not the real thing. Okay, so put a cheaper essential oil into a more expensive oil. And of course, the idea of sugar water, that's not flavoring necessarily, but that happens too. Again, well, let's sell some sugar. Let's think about corn syrup instead of honey or so on down the line. So there's a lot of opportunities here, but I'm talking about flavorings instead. The real analytical challenge is detection, like I say, small amounts of compounds. Usually, if you're looking for adulteration, you've got a food product. That food product has a flavor in that you question. Nobody gives you a bottle. The adulterating company doesn't give you this bottle and say, "You want to check this for me?" No, it's in a food product, and you're set out to say, "Is this real?" So you have the problem of trying to isolate the compounds out of a food product and do some testing on them to say, are they real or aren't they real? And so if you're looking at small amounts of compounds, differs within chemically identical molecules. So we may be looking for isotopes, we may be looking for enantiomers, and I'll go through that in a bit. So what kinds of tools do we use for this? It should be no surprise. GC, gas chromatography. LC, liquid chromatography. GCMS, LCMS should be in there. Isotope ratio mass spectrometry, and again, I'll come up with that a little bit later. What are we doing? Site-specific natural isotope fraction nuclear magnetic resonance spectrometry. So we're starting to look for isotopes like carbon-14, carbon-13. What kinds of ratios do we have? And for that matter, where in a molecule? This tells us about the isotope ratio, 13 to 12. And this tells us where those isotopes are, because nature puts things in a certain spot. Carbon-13 goes in certain spots in a molecule. And it depends upon what type of plant, what class of plant, where that molecule goes. So we get down to looking at the molecule itself and where isotopes, typically carbon-13, are. We also do carbon-14. Plant material is going to have radioactive C14 in it. It's been made from petroleum sources, synthesized artificially. Carbon, C14 is long gone. So again, a fairly simple and easy one to get around is looking for carbon-14. And so there's, like I say, some fairly sophisticated techniques where you start looking at these components. Because like I say, it will be benzaldehyde. And okay, what is different about that benzaldehyde than another benzaldehyde molecule? As an example. This is long ago. Long ago, people weren't sufficiently sophisticated, and maybe it still happens, but we hope not. And this is where companies would buy authentic artificial flavors, good, authentic artificial flavors. They make artificial flavors, and then they'd go ahead and add the artificial flavor to their flavor and sell it as a natural. And so that was actually quite a good business. You want a good cherry flavor? I'll buy that from fermentation. Pick a company, and then I'll rebrand it, and I'll sell it as a natural flavor someplace. It seems pretty straightforward, but it was done. So it was done. And so what you would do is, if you're trying to catch somebody at this, you'd be looking for, ethanol. That's not really good knowledge. But you'd be looking at the food or looking at the flavor for triacid and triethyl citrate or propylene glycol. Those materials are not natural. You wouldn't be using them as a solvent in your natural flavor. Where did they come from? They came from the cheap artificial flavor you bought. That's the solvent for this artificial flavor that you dumped into a natural flavor. So that's so simple. People tend to look for it. When I say ethanol, well, ethanol can be natural, so that's not a good choice there. But you would ask, well, where does ethanol come from? Okay. So that's a simple way. Non-natural constituents. There are some compounds that haven't been found in nature. And so in that case, something like allyl caproid doesn't exist in nature. Well, I take it back. It was found once in early 1960s in potato. Never been duplicated, never been found by anybody else in the world, but one research group found it. So if it's a natural flavor, and that happens to be grape pineapple, by the way, that's not what nature uses to reproduce pineapple, but it's a nice pineapple character. And so if you find that in a pineapple flavor, it's natural. You say, well, nature doesn't make that. Okay, it's not going to be so good. Ethyl maltol, you're into jammy, you're into heated berry type flavors. Well, maltol's nice, maltol's natural. Ethyl maltol's never been found in nature. So, but it makes a nice combination. If you put ethyl maltol with maltol, it's a better character. But okay, that's not natural. So that can't be natural. So scratch that one, scratch that one. Ethyl vanillin. Most of your artificial flavors, vanilla flavors, are a blend of vanillin and ethyl vanillin. They fit together really nicely, but ethyl vanilin's never been found in nature. So again, what you do in some flavors, you look for things that are not natural, can't be natural. They really fit well in the flavor, but they're not there. I was thinking one other example that we just went right by. So, you look for certain flavors, you look for certain compounds. And if they're there, you nail them to the wall. There's no way they can come from any natural source. Gas chromatographic profiles. Some companies do that and have done that. They simply do gas chromatography of the flavor that's sent to them. And they'll get a profile of that flavor. And every time it comes in, they simply run an analytical, okay, here's the profile, these are the compounds, look at that same pattern, they're happy. But the problem is that sometimes they do change, and that profile can change slightly due to contaminants in the ingredients. A flavor company may be buying a chemical from Sigma, Aldrich, natural flavors, and they decide they're going to buy from Comex instead. Well, that chemical, the name chemical's there, but there's impurities along with it. And so you could be having different gas chromatographic profile from changing buyers of one of your materials. And so this doesn't necessarily mean if you've got this profile, and you get a different one, unless it's really weird, that you're suspicious. You start looking and say, what else can I find? Okay. Or the company say, why is your flavor profile different now? It used to be like this, and have that explained to them. In some cases, this is for a flavor, and it can be an essential oil too. So it can apply to either one, flavor or an essential oil. It's a profile. In some cases, and these are for now essential oil of celery, should have 7 to 7.5% beta-celanine in it. If it doesn't, there's some other oils you can blend that still give a pretty nice profile. But the only place beta-celanine is found is in celery oil. It's unique. And so you look in that oil for that unique component that doesn't come in the other oil. And it should be around 7 to 7.5%. Again, one of the amusing things that I was sitting in a flavor company and there was some discussion going on. I was close enough to hear the discussion. And one of the people said, well, we've got this flavor and it doesn't fit the profile, that this component is wrong. And so you better tell them, no, there's a problem with this essential oil. It can't be real. So it's too little of this particular component. And so there's a few hours later, and another guy comes back in, he talks to them again. They send us over a new flavor. They ran it over by courier. We analyzed it. It's got too much. He said, okay, too little, too much. And they were hoping to get the right amount in there so they could say it's natural. It's weird. But anyway, so you look for something that's unique to an oil that you can then look for. In oil of peppermint, saponine hydrate is unique to that oil. Should be present about 1%. Saponine, there's beta-celanine in the other. And this is oil of corn mint. Oil of corn mint is fairly inexpensive. It's like mint. It has the menthol and so on, but there's a little bit of difference in one of the components. I don't know if I can. I'd have to go through it. I think it's this one, transacetyl hydrate. It's different. This is in oil of peppermint. I think it's absent from the oil of corn mint. So again, you look for things that are unique to the oil you want to buy. Uh-oh. Let's take a break. So how about coming back at 10 after? Good. So we've got a few minutes left. Let me see if I can look at one other thing. First, I got to be able to find it. So we'll probably do 10 or 15 minutes. How's that? And then we'll call it quits. Okay. Not behaving. So, one of the last subjects, I think we have got a couple other topics that we'll finish up with next time. But let me just spend a few minutes in this as an introduction. You don't have these, but you look at them. How's that? So I won't go very far with it. Interaction of flavoring substances with food ingredients. This is quite an interesting challenge. What we're looking at is things that will influence how flavors are given up in the mouth during the eating process. Um, and so if a flavor is in a food and it's tied up with some ingredient, whether it happens to be a protein, it happens to be a starch, sugar, one way or another, if it's tied up one way or another, it's not going to be released and you're not going to be sensing it. And so it's kind of why flavors taste different in different foods. As I think I probably mentioned, if you go to a flavor company and you want a strawberry flavor, you probably have 500 different strawberry flavors if they're a big enough company. 500 different flavors. Well, because citrus, there's different characters, right? You got jammy, you got green, you got all these others. But within that, you basically find that flavors interact differently with the matrix, the food they're put in. A flavor has to be designed for that food. You don't take a flavor that's made for ice cream and put it in a baked cake. It wouldn't taste anything like it's supposed to. Flavors taste different in different foods, and that's because how they interact with the food components. And so the idea is you might be out there and saying, well, gosh, I want I don't want to change my product, but I need to change my ingredients. I may want to swap out a gum. I may get a better price, a better functional ingredient and put it into my food instead. And so you might say, gee, I'd like to make some ingredient change in this product, but what happens when you change the ingredient? You're going to change the flavor. That's an interesting one. And certainly the whole idea of proteins and flavoring proteins is one that's really significant. Proteins are very reactive with flavoring compounds. And so when we're entering this time, or we're in this time, where people are producing high protein beverages, high protein everything, there's really problems in trying to get a good flavor that lasts in those products. So proteins, like I say, are exceptionally challenging. So the idea of how does flavor interact with your food components? There's some fairly simple ways. pH certainly has an effect on flavor. It's obvious taste. If you got a low pH, guess what? It tastes acid. No kidding. But you should also recognize that it can change the aroma too. Not only the taste, but it can change the aroma of the food product. And this is an example. I don't know if I mentioned in that the off flavor section or not. But if you think about something as simple as propionic acid, okay. That's a short chain acid. At low pHs, it's protonated, right? It's protonated. You go to higher pHs where it's not protonated, then it's sodium, it's a salt. This is a very water-soluble component. It's ionized, loves water. If we drop the pH, this is going to love water. This is going to want to evaporate. It's going to evaporate and be smelled. So when you put this into a food product, it's going to have a tart taste and an acidic aroma at low pH. You take exactly the same food system and you just bring it up in pH, all of a sudden it's no longer volatile. I don't get that volatile aroma. I don't get that character at all. And it's less acidic aroma, and it's less tart in perception. So I didn't do anything except I changed the pH of the product. So acidic compounds, they change with pH. Basic compounds change with pH. What are some basic compounds? Pyrazines, for example. Chocolate depends very strongly upon pyrazines for character. And so what happens when we put a positively charged basic compound? So this would be a low pH, it takes on this, and it's less aroma. So acids in low pH have more aroma. Basic compounds at a low pH have less aroma. So one gets less, one gets more. If you bring the pH up on some, we find that pyrazine or metamine will have more room. Have you ever wondered why it's hard to make a really good acidic chocolate product? It's tough to have a good chocolate flavor in an acid product. Why? Because what does chocolate get a lot of its flavor from? From positively charged compounds, those pyrazines. And so you drop the pH, and those nice chocolate notes, they simply disappear. They all take on a positive charge, and they decline. At higher pH, there they are. If they're all thinner, they're not charged, they're going to readily evaporate, and you're going to be able to smell them as you chew and swallow. So it's an example, again, of the effect of something as simple as changing pH of the product and why. pH also tends to affect stability of flavor materials. Although we usually don't get into the area of pH where we actually change flavor chemicals. We change maybe their binding, we change their solubility. We can do that pretty easily. But there's examples of hydrolysis of esters. So if you have a low enough pH, you could actually break down esters in fruit flavors. That takes a darn low pH. Again, terpene-based flavors get pH dependent on their stability. So we can get degradation, particularly of citral. Lemon flavor, very pH dependent. We didn't get the lemon product I wanted you to taste for lab last time. But if you ever have an opportunity, look for canned lemonade. So it's in a can or lemon tea. And you ought to buy one and taste it. And if you think that resembles lemon, let me know. The beverages are low pH. That low pH, the citral that gives this lemon flavor, is totally unstable. Give it a few days in that can, and it's gone. Now, people apparently accept that kind of thing because they keep on buying it. But this is not a fresh lemon character. Anything that's in a can has to be low pH, and it's not going to be stable. And the idea of reactions, so we could get Maillard reactions. We can have interesting things happening depending upon the pH of a product. So anyway, this effective protein binding may be pH dependent. So protein binding with flavors, and again, that's what one of the things Vaidy's looking at is how proteins react with flavoring. And he really finds a strong effect of binding of flavors onto proteins based on pH. And interestingly enough, they tend to follow the Maillard reaction. So these carbonyl compounds, very common in flavoring materials, they love proteins. They're going to react with those proteins very, very quickly. And again, the higher the pH, the faster they react. Interaction with lipids, and I probably get through this one and then stop. Well, interaction with lipids. Lipids are extremely important to flavor and how they influence flavor. They're not chemical reactions. So it isn't as though you have a chemical reaction between a flavor compound and a lipid. But the lipid influences the volatility, the desire of that chemical to leave the food and be perceived. So these lipids, flavors love them. They're going to stay in the lipid, and so they just don't come out for sensing. And this is, we'll see how we can do with this one. Vanillin it's both water soluble and oil soluble. It has a little greater oil soluble than water solubility. Diacetyl tends to be very, very water soluble. And so it's kind of interesting. If they have an oil and water mixture, where does this vanillin and diacetyl go? How do they partition? And so if we actually look at something like diacetyl, we can add oil to the mixture. We've got a blend of oil and water. We can add oil to it, and the diacetyl actually just tends to be uninfluenced by adding oil. If we look at something like vanillin and we start adding oil to a water system, we find that vanillin goes into the oil and it doesn't give enough for sensing. So it's rather interesting. I think maybe I don't have an example of that. But when you make ice cream, if you have ice milk, you don't need much vanillin. You don't need much vanillin. But if you get into 10% fat ice cream, you get into 14% fat ice cream, you have to jack up the vanilla flavor. You may have to double or more of the vanilla flavor because there's oil. That oil solubilizes the compounds, vanillin compounds. They don't come out for sensing, you don't perceive them. So it's really fascinating how that happens. And this is one that I particularly like, and we'll stop after this one. So this is simply where Jean-Paul, some of you know Jean-Paul fairly well, this was part of his thesis. But this was at a time when low-fat was the craze. Everybody was going to produce low-fat products and going to be wonderful, and we're all going to be happy. And it didn't go that way at all. And so what he did is he put diacetyl, limonene, propanol, or ethyl heptanoate in water. And then he measured how much comes out of the water for smell. And so if there's no oil, this much diacetyl came out for smelling. He added a 10% oil, made an emulsion. Oh, dropped a little bit, dropped a little, dropped a little. You had to get out quite a ways, 5 to 20% oil, before it really decreased the diacetyl. Because diacetyl is like oil. It's kind of indifferent to it. However, look up here. If we look at ethyl heptanoate, a fruity note, 0% oil, okay, that's the perception you would have. You're really high. 10% oil, well, that dropped some. 1%, what is it? Maybe 30%? So you lost 70% of that aroma character by going with 1% oil. You go out here to 5, 10, 20% oil, and that flavor just disappears. That compound doesn't show anymore. And that's the same over here for limonene. Limonene, remember, is citrus oil. How quickly it drops off. So water-soluble materials such as propanol, which is a flavor compound, diacetyl, they don't care how much fat you've got in there. They're pretty indifferent to it. But some other components really are lessened when you put fat into the system. And so that's where you get yourself in trouble, is that when you go to low-fat products, there's nowhere for these some of these compounds to go. We're kind of used to limonene or this character being reduced in chocolate. Okay, high fat level, we don't really expect to be limonene. We don't notice that. We wouldn't even notice the ethyl heptanoate. Take the fat out, and you've got the same chocolate flavor, knocks your socks off. It was down here, you were happy with it. That's what you got used to, a low level of these compounds. But now all of a sudden, they're just forced out of the product. And so this whole idea of a low fat, there's no place for the flavor to go. The chocolate flavor was formed by roasting and so on. It partitioned between the fat and the water. It stayed put in a certain balance. So as you took the fat out, there's no place for the flavor to go. In certain parts of it stuck out like as a sore thumb. So it's really a fascinating problem. Well, like I said, we're going to quit. So I will send this to you. Also, probably Monday as usual, right? Okay. Anyway, have a good week.